Alright, the thunderstorm, some ingredients needed for a storm is buoyancy and instability, which is the force that causes the air to quickly rise, usually from the heating of the earth. Okay? That's one of the things we need, is that warm, moist air rising to produce storms. You need a lifting mechanism, which is a way to make the air parcel rise even faster. Some of the things that qualifies that are heels, fronts, jet streaks. A jet streak, by the way, is not a jet flying through the air in that trail you see. It's a higher band of winds up in the atmosphere at the level, at the jet stream level. That's all it is. A piece or area of even higher winds within the jet stream. And then strong heating can also provide a lifting mechanism, or qualifies a lifting mechanism. And you've got to have moisture. You know, you're not going to get clouds if you don't have moisture. It's kind of the easiest one. And then shear. So 4 things: buoyancy and instability, lifting mechanism, moisture, and wind shear. And we know from our regular class, wind shear is a change in wind speed and or direction with light. All right, buoyancy and instability. If the bubble is warmer than the surrounding air, it will continue to rise. That's the bottom line. So as long as it's going up through the atmosphere, if it's still warmer, it will continue to rise. So the warmer it is here at the ground, the higher it's going to go up, and the higher it goes up, the more intense that storm updraft is going to be, and the better chance of that storm producing severe weather. So that's why we watch it closely. How quickly will it rise? Again, the greater the drop in temperature as you go up in the atmosphere is going to allow that air parcel that's moving up to move up even higher and move up even quicker. And that's why we really want to know, when we look at the atmosphere, how quickly the temperature drops as you go up. Something you don't need to know is called the lapse rate. That's the rate of temperature decrease as you go up. It always decreases. Even in the dead of summer, if you go outside, if you could stick your head outside of an airplane at 20,000 feet until it dies, it would be below freezing. If I don't care if it's 105 degrees down here, it's below freezing up there. So the temperature always decreases, but what's important is how quickly it decreases as you go up. And that decrease, the quicker it decreases, the faster developing thunderstorm updrafts can go up. Because it's warm air at the ground, and it's going up to relatively colder air as it goes up. Even though it's cooling as it goes up, if it's still a little cooler than the air up there, it's going to continue to rise.
Yeah, I noticed on last Thursday we had some really big lapse rates on that one, all the way down to a -10.
Yeah.
It's the first time I've ever seen that here.
Yeah, and that's something. It's just another thing. You know, you can dig into this stuff as little or as much as you want, but you know, if you look at that and get used to that, and the Storm Prediction Center talks about the lapse rates all the time, that's something, just another thing you can kind of key on to know what the concern is. But a very common thing you can key on is the CAPE, which stands for Convective Available Potential Energy. And that yellow handout that I gave there, that's just for fun. I mean, you might throw it away or you might use it, but you can actually, there's numerous places nowadays you can get the CAPE, including from the Storm Prediction Center website, and you can get a feel of this buoyancy deal I'm talking about. You know, how, strong can the storms get based on the buoyancy. And I'll show you the values here, but the higher the CAPE, the stronger the updraft. The higher the CAPE, the stronger the updraft. So large CAPE equals large updrafts, a lot of buoyancy. And here are the numbers. These are the CAPE values, that little yellow chart you have there. It's on there. But like 1,000 to 2,000 is considered moderate buoyancy. That could produce a storm updraft of about 50 to 70 miles an hour on average with a CAPE of that value. So it's kind of fun because we can measure this. And that's based on the data we get from the weather balloons we send up, and from aircraft that's up there that sends us back data and so forth. So, an extreme buoyancy would be something like over 4,000. The updraft speed on a storm like that could be in excess of 100 miles an hour. So that's why we want to measure that. The stronger the updraft, the more likelihood the storm is going to be severe. And if you look on the Storm Prediction Center website or some of them, there's going to be several layers of CAPE and different ways they measure CAPE, like most unstable and 0 to 1 kilometer, 3 kilometer, whatever. But the 0 to 3 kilometer is kind of a layer that's really probably one of the best just to look at these values to help there. But one thing you really need to know is that the CAPE is very seasonally dependent. In the wintertime, it takes hardly any CAPE because the wind fields are so strong that they compensate for the lack of instability or the lack of CAPE. Even 100 or 2 CAPE in the winter, we've had tornadoes with values that low in the wintertime. And the CAPE, by the way, it's kind of the what am I trying to say? The most common way of measuring the buoyancy ability. There's numerous others on that yellow sheet, like lifted index. That's one that's been around forever that I used when I first started doing weather. All right, boundaries. Sometimes an extra source of energy is required for storms to become tornadic. Boundaries can provide that in terms of wind shifts, temperature, moisture differences, and differential heating. This is a boundary right here from satellite imagery. There's a boundary, outflow boundaries. We talk about the rotors class out ahead of storms here. The tornado, by the way, developed right there, right where this outflow boundary intersected the storms. So they're important. The bottom line is most boundaries contain energy which can be used by thunderstorms to intensify and possibly produce energies. I repeat that. Most boundaries contain energy which can be used by thunderstorms to intensify and possibly produce tornadoes, even on days that tornadoes may not even be forecast. They're that important, so we have to watch boundaries. What happened here? I couldn't tell you off the top of my head if tornadoes were forecasted or not this day, but nonetheless there was a boundary that intersected and a tornado, a weaker tornado was falling. Here's just another example, outflow boundaries from these storms here. Had a severe thunderstorm warning there that's issued that moves to the southeast. South here, fire up. Here's the boundary. Here's another. It's something you have to get used to looking for. Here's another boundary right here. Outflow boundary from these storms up to the north. So we watch those very closely. All right, moisture is fuel for storms. You've got to have moisture to have clouds. You certainly got to have storms. Severe storms are more likely with dew points at least 58 degrees. Not an issue in the summer, generally not from this time on through the summer, but in the wintertime it is. I mean, that's kind of the threshold. So if the dew points only get up to 52 or something in the winter, even if we have thunderstorms forecast, we probably don't have to worry about any severe storms. It's 58, it's 57, 58, right in there is kind of the threshold, the very minimum that's needed. Storms need more moist air. The lower the dew point, the less more moist air is available, and therefore the less likelihood of severe storms. Location of the moisture through the atmosphere is important. Lack of moisture, for example, in the middle of the atmosphere can actually enhance the threat of severe weather. It kind of helps the updraft and everything, and it can even result in strong downbursts, damaging wind events here at the ground. Wind shear, we talked a lot about that in the first class. I won't say a lot about it, but there's wind directional shear and wind speed shear. Wind directional shear is a change in wind direction as you go up in the atmosphere, in this case southeast or west. Wind speed shear is an increase in wind speed, in this case from 15 at the ground to 90 at the top. And that kind of causes horizontal rolling in the atmosphere, and then that can get lifted by the upward moving air in the storm's updrafts, and that is kind of one of the things we think can lead eventually to tornadoes. So wind shear is very important. And here's basically what I just said, getting lifted up. in the vertical, and then once you have that in the vertical, it's kind of, the storm gets to spinning, it's kind of like the ice skater pulls their arms in, rotation gets faster and faster. If that happens to the storm, it can eventually produce a tornado. Good thing, just like the Cape, with the instability, with the wind shear, we can measure that through several different things we use. Here's a few of them, 0 to 8 kilometer shear, 0 to 6, just different levels of atmosphere. 0 to 3, for example, that's about 10,000 feet, 3,000 meters is about 10,000 feet. But generally, the stronger the shear, the better chance to have organized areas of severe weather. Now, we have a very specific thing that we use, and this is on that yellow sheet too. We're going to play around with it called velocity, specifically something called storm relative velocity, or SRH. And if we have values of that greater than 150, that's kind of a threshold for tornado formation. Doesn't mean one's going to happen, but you've at least got, if you're up to that, you've at least got the possibility of enough wind shear to produce tornadoes. So that's something we look at. We look at the Cape and we look at the velocity a lot. If you only looked at two things and just got used to the numbers a little bit, that's what you could look at, the storm relative velocity and the Cape. And it would make some sense to you and help out possibly. But it's really a combination of the Cape and the shear that determines if we get severe storms and if they're tornadic or not. And one can compensate for the other. In the wintertime, as I said, we have strong winds, and that compensates from the lack of heating. In the summer, we have obviously very strong heating, but we have weak winds, so it can compensate as well. In the spring and the fall, that's when we get just the right combination, unfortunately, sometimes of both of them, and that's why we have more severe weather and more tornadoes in the spring and in the fall. But here's an example. The wind shear in the wintertime is way up there, but the instability is low. And these are all these dots are severe storm events. And in the summertime, just the opposite again, lots of instability, but very weak wind shear. Just want to point out it's very seasonally dependent. One compensates for the other though. The spring and fall are just kind of the right time of year for that. Okay, summary, thunderstorms need warm, moist air to survive. The right combination of instability or Cape and winds changing direction and speed enhance the ability of the updraft to be stronger and to rotate. That's the bottom line of all I've been talking about there. Okay, with that, let's stop and take a 10-minute break. Don't spend a lot of information. Everybody rest the brains a little bit. We start back. As I see y'all are lighting, it's dark outside now. So here we have a wall cloud in the upper right picture there that's rotating, obviously. And the one at the bottom right here, the wall cloud with the tornado, it's also got a pronounced tail cloud, which is a pretty common component of a wall cloud that's well developed. Sometimes in the plains we get more classic looking supercells than here. Here we get a lot of moisture from the Gulf of Mexico, and sometimes they're quite hard to see or get a little bit more mottled as a result of that. But a very key thing is to look at the cloud fragments, the lower base, under the updraft to see if it's rotating, just like in the little video clip we just saw. Watch for that rotation. All right, as far as tornado formation, there are three primary ingredients. It generally follows this process. Development of a persistent, rotating updraft. So the persistence, and that's something when we're warning back in the office, we're looking for that persistence. We're looking for a little bit of continuity of time, because if we don't, we'd be issuing a lot more tornado warnings than we do. We're looking for that persistent rotation, and we're looking for a depth of it too, back at the office on radar. So we're wanting to see that persistent rotating updraft. Next is development of a special rear flank downdraft that contains rotation to aid in the development of the rotation downward toward the ground. So it's the, what we call the RFD, the rear flank downdraft. In our regular class, we talk about the downdraft, but we're talking about the forward flank downdraft. We just didn't give it the name there. So that's the downdraft you have with every storm is the forward flank. For the supercells, you can get something called the rear flank downdraft. And then thirdly, is focusing on that low-level rotation through convergence and upward spin up into the updraft. And that's the diagram, the first video after the break, and before that I talked about, that's what that was all about. But all three ingredients must occur in concert to form significant F2 or higher tornadoes. Weak or short-lived tornadoes can occur within supercells or non-supercells without all three ingredients. But again, for the supercells, especially to produce the F2 or higher tornadoes, you've got to have all three of those things in place for that to happen. The RFD, this little video clip about it. Whoops. There. For some reason that would not play. But here's the clear slide. It is playing. Good. And it may be visual as the RFD, which is back here. This is looking west, okay? And we're looking in for this area here. Okay, in this area here we have the wall cloud, so we're looking for some brighter colors back in this part of the wall cloud back here. That's what we call the clear slide. You can see it's brighter. That's this downdraft coming down here, eating away at the clouds, drying them out. And then here we have some more of it as well. All right, and this shows it, the rear flank downdraft right here. Let me back up. You can see it's brighter here. This is probably really the best, simplest indication of it right here. But normally this would be dark, and you can see it's brighter back here. Again, this is looking to the west. This whole thing is the wall cloud, your tornado course there. And the reason it's there, we think, is because this rear flank downdraft is pushing this rotating updraft toward the ground. That makes sense?
I had a real quick question going back to the previous slide with all three ingredients or with forming an F2 or higher. Was that based on the original Fujita system or the enhanced Fujita scale?
Let me think of which one you're talking about. What I was talking about right here, probably all three ingredients. It's really the same, anyways, pretty much. The damage caused by F2 or DF2 is essentially the same. What we've done is reassign the winds to those damage parameters. So it's a good question, but it's really kind of the same thing. Okay, so there's your RFD once again. Here it is again. Here you can see it's brighter here. Wall cloud tail over to the right, to the northeast. All right, so in summary, the RFD translates the rotation to the ground. Upon reaching the ground, some of the RFD flows around and into the low-level updraft vortex, while other air flows away from the vortex. And because of that, right there really is why we have cyclic supercells. It's because we have that air wrap around the updraft. It eventually chokes off the updraft, that rotating updraft, and that's when the tornado ropes out, gets real thin, contorted, and eventually dies, and then maybe another tornado develops on a piece of there. Sometimes the RFD causes a storm scale circulation or something focused near the ground and cut off the level rotation, basically what I just said. The updraft must continue to persist as the RFD develops and concentrates the rotation below it. Thus, the longer an updraft persists, the more likely tornado formation becomes. So that's why we don't like storms to hang around, because if they hang around, And that updraft, and if they are hanging around, the updraft is persisting, and that is going to increase the likelihood of tornado formation if we have the three conditions we just talked about. But we still have a lot of research to do on that. That's our best understanding.
When the tornadic circulation reaches ground, an ample supply of warm, moist air flows into the tornado. After impacting the surface, the RFD wraps around the tornado, gradually cutting off the inflow. Intense downbursts often result from the RFD's gust front as it progresses around the right flank of the tornado. Because its inflow is disrupted, the tornado begins to decay. The condensation funnel decreases in size, tilts with height, and takes on a rope-like appearance before dissipating. After this so-called occlusion of the mesocyclone, subsequent mesocyclones and tornadoes may form further east, resulting in a cyclic supercell.
And cyclic supercells are kind of the norm. Really, if you have a supercell, often it is cyclic. Okay, outflow. We talked about that in the basic class a lot. But we have the gust front, which is the leading edge of that outflow. We have with every storm that's at the boundary. And we showed with radar imagery earlier, of course, the shelf cloud is what you see cloud-wise that coincides with the gust front. The downdrafts, the forward flank, and that's, anytime we talk about downdraft, we don't give the name. We're talking about the forward flank downdraft, because every storm has the forward flank downdraft, or one downdraft. But only, generally the supercells have the RFD, real flank downdraft. But they are produced by a combination of downward momentum from falling raindrops, from the frictional drag that air is pulling down, being pulled down with the raindrops, and also the dry air brought into the storm as it evaporates. Some of the precip cools the air, the water vapor on your, just like on your skin, and it wants to sink when it cools. So the more that's evaporated, the stronger the downdraft becomes through that process called entrainment. So there's two factors then that produce the downdraft: the frictional drag and the evaporation. And this is a wet microburst. It occurred out in Kansas. You'll see there it comes. The blob of, yeah. Now this is sped up a few times, but that's bad if you see that even in slow motion. That's a downburst happening. And downbursts, again, if they're less than 2.5 miles across, they're microbursts, which is the vast majority. And if they're intense, long-lived downbursts, they are the variety that we had here May 9, 2009, which is called the what? The ratio, yeah. The downdraft area, downbursts occur when we have the downdrafts get strong enough, then they're a downburst. Rapid downward motion, a flare appearance near the ground, the rain foot, and again, they're less than 2.5 miles, they're micro. If they're greater than 2.5, they're macro bursts. And here's curls with some of the downburst. And here's just like the one that occurred here. We had one a couple of years ago. Produced softball size hail and winds to 110 miles an hour. Bottom line, downburst can be some really bad dudes. Okay, Mike's ready. Any questions about anything I've covered? I know it's a lot of material in a short period of time. Mike's going to take you through spotter positioning. If you're doing some mobile spotting, you have some good things there, and then the radar section.